Hello, good afternoon, friends. I'm again here with you for the paper number 13, that is solid state physics, and myself, Dr. S.D. Chauhan from Department of Physics, Adarsh College, Hingoli. Yesterday, we have seen syllabi related with the paper number 13, that is what four units, which type of the four units we are going to learn in this solid state physics is to be there. The first one unit, that is crystal structure, and which contains the crystal lattice and the translation vector, unit cell, basis, symmetry operations, point groups, space group, types of the lattice, simple crystal structures like and diamond, NaCl, and some problems we will see. Let's come to the first part or the first unit, that is the crystal structure. Now, to understand the what exactly the crystal is to be there or the crystal structure is to be there, it's simple way: the solids, liquids, and the gases are the three stages we have states we can see in our universe. Basically, wherever the smallest small part, that is the atoms or the molecule, is strongly bonded with each other, that gives you a definite shape and the size is to be there, and that is nothing but to be called your solid is to be there. And as far as the atoms and the molecules are not strongly bonded with each other, that time they are loosely when bonded with each other, they are not having a definite shape and the size is to be there, and due to that these are called as your liquids. Now when this bonding becomes much more lighter, or the very weak, in that case the such type of the state is nothing but to be gaseous state. And that's why we have seen in the universe number of solids are having definite shape and the sizes are to be there, but as far as the liquids is to be, we can see whatever the shape you are having, the liquid having that type of the shape is to be there. But as far as gas or the gas molecules, we have seen in the container, the gas always we can see in the container, and that gas molecules are always in the agitation mode. That means wandering here and there from one place to another place continuously, and that is somehow the gas molecules are wandering because of there is no strong bonding in between them is to be there, and this somehow gives differentiation in between the solid, liquid, and your gaseous state is to be there. Now, as we are learning here the paper that is called solid state physics, and actually it is the branch of the physics which deals with the physical properties of the solids, not only physical property of the any solid but the atoms, and inside that how the electrons are moving or their behavior, that also we are going to learn, and that is what it is called as your solid state physics is to be there. Now, the solids are of two types, and basically you are also aware about that the crystalline solids and the non-crystalline solids. As far as the crystalline solids are concerned, it is regular or the periodic arrangement of the atoms are to be, and in that case the regular or periodic, that means the atoms, one atom is here, another is at a fixed distance, another will be at a fixed distance in that same row, and that is somehow the your crystalline solids are to be there. And here the regular or periodic arrangement of the atoms, we can say or we can call it is as a your simply as an crystalline solids. Now when such type of the crystalline solids are going to be formed, that all the such type of the regular or the periodic fixed arrangement or the order is to be there for your atoms, in that case the such type of the solids releases much more energy, and due to that the crystalline state is low energy state, we can say. Again, the crystalline solids are again differentiated in the two parts. One is to be single crystalline and another is going to be polycrystalline. So first see that is what exactly the single crystalline. The single crystalline is what? The simply one regular or the periodicity, no doubt, as far as this single crystalline is also the form of your crystalline solids. That means the regular or periodic arrangement of the atom is to be there. But in the single crystalline solids, this periodicity of the atoms extended throughout the end of the material. That means it will be similar till the end of the material. Whatever the small part you will take of that material, you will find the same periodicity or the arrangement of the atom is to be there. Whatever the part you will take from that solid, you will find the similarity or the uniformity in between the periodicity as far as the atoms are going to be concerned. And the such type of the materials or the solids are nothing but to be single crystalline solids are to be there. And basically you have seen the diamonds are the example, quartz crystal and the mica are the simple example of these single crystalline solids are. And wherever the second part or the single crystallines is the one part and the polycrystalline is the another part of the your crystalline solid. Now when these types of these particularly crystalline solids, when we are going to be differentiating, the polycrystalline is a little bit different from the your single crystalline. Now what exactly the difference in between this single crystalline and the polycrystalline is that in the single crystalline solid you will see a similar atoms at a fixed, and the periodicity is going to be fixed one, and that will be throughout the end of the material. But here in the polycrystalline solids, it is nothing but the aggregate of the number of different shapes of the crystallites. Now as far as the crystallites are, maybe triangle, maybe square, maybe rectangular, or maybe hexagonal. Now these are the different shapes is nothing but to be your crystallites. And this random arrangement or the random aggregate of such type of the crystallites are nothing but to be your polycrystalline. And this type of the polycrystallines are basically is nothing but to be random. It is not fixed that after the triangle the square will be there, after the square there will be a hexagonal fix. Randomly it will change. After the triangle there will be square, after the square there may be a rectangular. All these things are going to be continuously randomly arranged, and such type of the arrangement aggregate of the your in the crystal is to be there. That is nothing but to be called your polycrystalline solids are to be there. Now with this case, the whatever be the small crystallites are to be there, it is called as a grains. And whatever the boundaries, when I can say the triangle is to be there, it means it is having fixed boundary. When I can say a rectangular, that means it is having the fixed boundary as an rectangular. We can when I can say a square, that means here it is having the fixed square size is to be there. That means boundaries are fixed, and such boundaries are nothing but to be called grain boundaries are there. And basically examples are metals and your ceramics are to be there. Now as the crystalline solids we have seen, that is containing two parts. The another part that is the called as a non-crystalline solids. And definitely in the crystalline solids we have seen periodic and the regular arrangement is to be there. But definitely in the non-crystalline it is opposite to that. That means in the non-crystalline solids the atoms arrangement will not be regular or periodic, it is random. And that's why non-crystalline solids are those the random arrangement of the solids are to be there. And that's what exactly the your non-crystalline solids are to be there. And basically you can see in day-to-day life the glass example for these non-crystalline solids, that is glass, rubber, plastic. And that's why you can see why these non-crystalline solids are very easy to make a different shapes of the particularly it is when the arrangement is random, it is very easy to break. But when the arrangement is regular, it is very hard to break it. And that is why these type of the examples that shows glass or the plastic or the rubber is to be there, that having very easily we can mold in a different shape, because these are randomly in these, the atoms are arranged randomly, not regularly. And that's why it is becomes very easy to adjust wherever I like it. Now, as the crystal structure we are learning, when the particularly you can say the area of the interest in the crystallography or the crystal structure is going on increasing, due to that the another sub branch is going to be developed, and that is called as a crystallography. And that gives you some sort of study of geometrical forms of physical properties of the crystal, and that related with the crystal structures or the crystalline solids are to be there. That is called your crystallography. And this crystallography gives you some sort of a definite learning about the crystal structure, how the different types of the crystals are to be there or crystalline solids are to be there. Now, looking forward, as far as the crystal, the one another part, that is crystallites and the translation vectors. Now, in this section, now first we have to understand what the crystal lattice is to be there, and translation vector is to be there. And to understand this, first we have to understand the relation between the imaginary points and in the space and the atoms in the crystals are to be there. Now, wherever we can see a star or the particularly different empty space in the sky, that time we can see the imaginary points in the sky. And when I want to fix that point, I need a particularly fixing that point, a different category or cardinal system is to be there. And in this case, these imaginary points and wherever the solids are going to be concerned, the atoms were going to be arranged, there is some relationship in between them, where the imaginary points and these imaginary points when matches with particularly your atoms in the crystal, that somehow the relationship for your lattices. And simply lattice is what? Lattice is nothing but to be net type arrangement of the atoms are to be there. And that's why this imaginary point and this your atoms in the crystal in the your solids are having the similarity in their arrangement. And wherever the atoms are arranged in such type of the net like of the arrangement is to be there, this such type of the particular solids, again we can say a lattice for that case. And the lattices, when we want to particularly two dimension, whenever the lattices are to be atoms are going to be arranged, when the I can say in the imaginary part or in the space I can say, then I have to, if I want to define any point in a space, I have to take it three-dimensional case. If I, as you know, the cardinal point system is to be there. Now, when I want to define the position of that one point in a space, I need a three-dimension case: x-axis, y-axis, and z-axis is to be there. And in that case, that means to be where I need a three-dimensional case in the space. In similar way, when the atoms are arranged in the such type of the solids are to be net type arrangement is to be there. And if I want to define that position of any atom is to be there, I need to find out first. That's why I have to I found relationship in between the imaginary points and your atoms in the solids are to be there. Now, when I consider in a two-dimensional or the three-dimensional case, wherever simply one-dimensional array is nothing but to be one array, you can say, means the atoms are supposed to be arranged as far as the crystallites we can say, or the crystalline solids are to be there. The first atom is here, another atom is here, The third atom will be definitely after the same distance periodicity as crystalline solids are to be there. Now this is if suppose in the one direction all these things atoms are to be there, it is called one dimensional array. But if suppose with respect to this point there is another one point, or the one atom is to be there with respect to this point, another atom, this is suppose along the x-axis, along the y-axis there is another atom that is around surrounding this, similar to this, then in that case the whatever be the atom is arranged in such fashion, it is two dimensional arrays to be there. And in this two dimensional array, and arrangement of the particular your infinite number of the imaginary points in these uh, dimensional space, with each point having identical surrounding, is called your point lattice, or the space lattice is to be there. As two dimensional array is to be there, that means this way and this way, that is to be two, where I can say in this way, this is one and this is another two, this is x-axis, this is along the y-axis. Now at the same distance periodicity is going to be uniform. Similarly here again one another part is to be there, that is the vector is to be there. Now in this case, the along the x-axis, along the y-axis, this is two dimensional case and it is continuously with respect to this point, again here will be there, again another one, again one, it is going on, that will give you me one paper plane is we can say. And in that case the what type of the arrangement is to be there atoms in this space imaginary points are going to be matching, that is aggregate of such type of the, when we can say the lattice, it is net type arrangement. And such type of the arrangement of the your atoms in imaginary space in the two dimensional case, in that case each point means after this each point having identical surrounding. Now what exactly the identical surrounding, that is very much simple to understand. Identical surrounding lattice or the identical surrounding is nothing but when we can see the similar point, or this one point, this point and this one point, from the both view we will see means either I am moving it from this side or this side, when I can moving this lattice is to be there, net type arrangement is has the same appearance will be there from the this side. If I have the cube suppose, from this side I will see the 4 points likewise this, and if I am changing opposite direction I will see the similar cube in that fashion. That means either viewing from the front or the back side, it will be looking like to be same. I mean the both way, I mean when the lattice, that means net type arrangement of the atoms, I can see from the front side or the back side, it appears me similar. And such type of the atoms or such type of the points are nothing but to be identical surroundings, called it as identical surroundings. That means in the space lattice or the point lattice, that means in the two dimensional case, when the points are arranged in a regular and periodic is to be there, but in two dimensional case, when these points where the two dimensional points are in the imaginary space are to be there, and they all are having the identical surroundings, such type of the lattice is nothing but to be your point lattice or the space lattice is to be there. Now as far as in the dimension point of view, or the such type of the additional r and r vector that we will see in detail in the my next slide is to be there. As such type of the lattice contains a small group of the points, that is nothing but to be called your pattern unit. And the group of this pattern unit, here you will see basically very simply you can understand what exactly I am meaning to be there. Here if you look at, it is a two-dimensional figure, or the points or the atoms are arranged. If you look at here, the one vector that is a1, another vector that is b1 is to be there. Just think about this. And in this case a1 and the b1, that is uh, having the another point giving it r and r dash, where r and r dash, that is r and r dash is giving you basically 2 points, or the r and r dash both are having identical surroundings. If I am looking for the crystal from this side, R will be similar look like. If I am going back side, it R dash will be having the similar view, and that's why R and R dash are nothing but to be called your identical surrounding points are to be there. This structure we will see in detail also next part. And here when I am looking for the uh, another case where it is to be your translation operations are to be there. Here the relation or the repetition of pattern unit means group of the atoms in this case continuously going on. That means at this stage vector A and the vector B, O is nothing but to be your origin, first atom, and another atom it at a stage that is A1, another atom in another direction that is B1. This repetition or the arrangement of the atom is continuously going on, but as far as OA1 will be one vector, OB1 will be another vector, and that is somehow the repetition of this pattern unit, that means group of atoms are to be there, that gives you translation. Translation means that is repetition operation is to be there. And here T is nothing but to be given with capital T is equal to n1a plus n2b plus n3c is to be there. Here A, B, C are nothing but to be your vectors. That means in the three dimensional, when I am talking about imaginary point to explain, or that case A, B, C are nothing but to be vectors. But here it is related with the translation vector, and these are nothing but to be a fundamental vectors it is called. And as far as n1, n2 and n3 are arbitrary imaginary atoms, first, second, third is to be there. Now this translation, if you look at these points R and R dash, now R dash is formed here, the notification is a little bit taken from the book, that's why it is given a small R dash and the small r. Please consider it here as an capital one where it is shown in your diagram. Now here R dash is formed from the R, and that's why this is nothing but R dash is nothing but to be R plus T is to be there. And what is T? T is nothing but to be the translation, where n1a plus n2b plus n2c, this is what the three vectors, when I am defining any point in the space, I need three vectors or the three dimensional case is to be there, that is x, y and z axis. In that case the translation for the one atom, that is to be one translation is to be given, that is to be pattern is going to be repeated, and this translation when going to be added with R, that will give you the another point, that is R dash, having the same identical surrounding. And the point R dash can be obtained from the R, that is explained. Now the translation vector A, B, C are also called your crystal axis or the your basis vectors are to be there. Now here the first translation vector there for your example. Now the suppose the it contains an integral coefficients, that is translation is suppose 0a1 plus 1b1. In that case the whatever be the numbers are the integral coefficients are to be there, it contains, and that's why the R is going to be formed, that is R dash is going to be from the R plus T, and that is nothing but to be whatever be the vector or the translation vector which is produced or generated containing the integral coefficients. In that case the such type of the translation vector is nothing but to be called your primitive translation vector. And such type of the primitive translation vectors are going to be produced with the what vector, which vector contains integral coefficients, that is nothing but to be called your primitive translation vector. But as far as to understand the next part which is to be the first translation here, but here are the two translations in this diagram. And here if you look at this another case where the two translations are to be there, that is A2B2. If you look at the another case, A2B2 is to be there, And this A2 B2 translations are with the simply half A2 plus half B2, that is non-integral numbers are to be there. And that is why the such type of the R dash, that means identical surrounding number, is going to be formed. Such type of the crystals or the vectors, sorry, the translation vectors are called as a non-primitive translation vectors. And here, the whatever be the your translation vectors with the containing the integral value, that is called to be as an primitive translation vector. And whenever it is with the non-integral value or the vector, then it is called to be as an non-primitive translation vector. These are the basically where the your two parts, what exactly primitive and the non-primitive cases are to be there. In the simple way, to there are three vectors a, b and c are to be there. They are at a certain fixed distances are to be there. That means it is not necessary every time for the each solid it will be similar. It will be different according to what type of the crystal structures or the solids are to be there. And according to that, these crystal structures are the basically your crystals are somehow are in this fashion, or basically the your crystals are going to be differentiated, or the translation vector is differentiated in two parts, that is the primitive and the non-primitive case. Now, important factor with this case, with this translation vector, the unit cells are going to be produced. And what exactly meaning to be as an unit cell, and what type of the unit cells are there, that we will see in our next lecture. So till then, keep watching, be at home and be safe. Thank you.